Hello, everybody, and welcome to week 11 of Math 4400. So today we're going to talk about Fermat primes. And just to give you an idea of where that fits with what we've been doing the past couple of weeks. So 2 weeks ago, we started exploring squares mod p and discovering some of the rules that govern them. And then last week, we talked about how you justify those rules. First, we justified the rule for when -1 is a square mod p and for the Legendre symbol being multiplicative by using this formula that you could compute the Legendre symbol as n to the p minus 1 over 2 mod p. And that will come up again today. And then in this longer lecture for Thursday, when we didn't have class, we discussed how you justify the quadratic reciprocity law. Okay, so now this week we're going to give two applications of quadratic reciprocity. On Thursday, we're going to talk about the Lucas-Lammer test, which is something we encountered first and used in week 7. So this tells you when the Mersenne number is 2 to the L minus 1. So when is this Mersenne number a Mersenne prime? And so if you go back and look at week 7, exercise 3, and sort of some of the surrounding discussion, that's when we talked about that. By the time we just sort of stated the Lucas-Lammer test without justifying it. So now we're able to actually explain why that works. But we're going to do that on Thursday. Today, we're going to do something that looks similar, but works a little bit simpler. And that's going to be to study Fermat primes, which are sort of another type of prime number you build out of powers of 2, but in a slightly different way. Some similar ideas go into giving a test for when you have a Fermat prime, but they're a little bit simpler in this context. So we're going to do these first, and then we'll come back for Thursday to do the Lucas-Lammer test after developing in class some of the other related material. Okay, so that's where we're going. I just want to highlight in the Thursday video, we didn't give a full justification of quadratic reciprocity, and we sort of completely explained a few cases and then outlined the idea for how you would justify it in general, but didn't go all the way through it. However, both of these applications are only going to use the part that we justified completely. So in fact, both of these are only going to use quadratic reciprocity sort of for p over q and for the Legendre symbol p over q when p is equal to 3. So somehow actually that's something that was completely justified by what we did. And that's all we're using in these applications. Okay, so what is a Fermat prime? Well, a Fermat number is a number of the form 2 to the 2 to the n plus 1. Okay, so there's a lot of exponents here, but so you're raising 2 to the 2 to the nth power. And then you're adding 1 to it. So f0, that's 2 to the 2 to the 0. So 2 to the 0 is 1. So that's just 2 to the 1, which is 2, plus 1, so you get 3. F1, that's 2 to the 2 to the 2. So this 2 to the 2 would be 4. This 2 to the 2, this way. I did this wrong already. Sorry, when n is 1, this is 2 to the 2 to the 1. So this 2 to the 1 is 2. So you get 2 to the 2, which is 4, plus 1, so it's 5. So on F2, that's 2 to the 2 to the 2. Now you get that 4, and you get 2 to the 4, which is 16. And you add 1, you get 17, so that's F2. And you keep on going. And well, these get pretty big pretty quickly. But Pierre de Fermat, he investigated these numbers. And what he noticed is that, well, F0, F1, F2, and F3, and F4 are all prime. And those aren't so bad to check just by hand. Of course, F5 gets quite a bit bigger, so you might not want to check that. So sort of he basically stopped there and conjectured that these Fermat numbers are always prime. But well, in fact, sort of, he stopped a little too early. In fact, some people have suggested that he just made a computational mistake, and that's sort of why he didn't catch this. Because in fact, this very next one, F5, is a composite number. It's not prime. So as a factorization is 641 times something else. And when the key thing is 641 is not that big. And if you're going to conjecture a list of numbers are prime, you'd probably try sort of dividing by a few things at least. And well, you don't have to go that far to get to 641, especially because there's sort of some restrictions on what divisors of Fermat numbers can look like. And so that gets you actually to 641 pretty quickly. But this factorization was discovered by Euler 100 years after Fermat made this conjecture. So just goes to show that if you're willing to divide a few numbers, you can sort of disprove a 100-year-old conjecture. Good. And actually, what we think now is that most likely these Fermat numbers are not prime for any n larger than 4. So this is quite a bit different than when we were looking at these Mersenne primes, which we'll come back to on Thursday. So these Mersenne primes, you did 2 to the prime number minus 1. We saw that those were sort of quite often prime. In fact, like the largest prime numbers we know are Mersenne primes. Whereas here, it really seems quite likely that these Fermat numbers are not prime after sort of you get through these first 4 or these first 5. Okay, and these are just some numbers right now, so you might ask, why do we care? But these are actually sort of, and just like Mersenne primes were sort of interesting, for example, because Mersenne primes were related to perfect numbers. Fermat primes are interesting in relation to some other problems in number theory and geometry. And so there's sort of this classical, problem investigated like already by the ancient Greeks of when a regular n-gon is constructible using only a straight edge and a compass. So that means sort of you have sort of something that lets you draw circles and something that lets you draw straight lines, and you want to use those together to draw a regular n-gon. So like a regular just means all sides are the same length. So then all the angles are the same angle. Like a square is a regular four-gon. A like sort of regular pentagon looks like this. So those are all supposed to be the same length. It's a regular 5-gon. Turns out you can construct a regular 5-gon because this Fermat number F1 is 5. So you can construct a regular 3-gon, a regular 5-gon, a regular 17-gon, a regular 257-gon, regular 65,537-gon. You can't construct a regular you can't construct a regular this-gon. In fact, there's sort of a complete classification of when you can do this, which is really interesting. This is something the ancient Greeks didn't know, and they knew lots of things that you could construct, but they didn't know what the limits were. And it took till work of Gauss and Wansel to show that a regular n-gon is constructible with just a straight edge and compass if and only if n has a factorization where it looks like 2 to some power. So that can be sort of any power of 2. And then the other prime factors all appear to just a single power. And each of the other prime factors has to be Fermat prime. So if we think there are only 5 Fermat primes, so if we think sort of these are the only ones, then that sort of tells you like there's only actually like finitely many odd n that you can such that you can construct a regular n-gon with using only a straight edge and compass. And this is a really beautiful, really beautiful link between sort of some fundamentally geometric construction like this, the geometric idea, like constructing sort of an n-gon with equal length sides, and sort of something about prime numbers. So it's really quite a beautiful fact. And the way you justify this interesting fact was, well, it's well beyond the scope of this course, but it's something you can learn with basically undergraduate mathematics now. Like if you took a course in abstract algebra where you learned Galois theory, you might not learn this fact, but you would learn all of the tools you needed to sort of read a justification of this fact, for example. So this is the amazing progress of mathematics is something that puzzled the ancient Greeks and was unsolved for thousands of years. Somehow you can take like 1 or 2 more courses after this and then open up a textbook and learn it for yourself. Okay, so, but somehow like, Fermat primes are not just sort of interesting because Fermat made this conjecture, like they're connected to this interesting problem and sort of other interesting things. Okay, so, well, so how can we think about this? And say we want to check whether sort of more Fermat numbers are prime. It's sort of hard to do it by brute force because these numbers get very big. I mean, we already saw that sort of, well, okay, the first few weren't that big. I mean, even at 4, it's less than 100,000. That's sort of, you could spend a day just dividing by that by numbers to check it was prime. It'd be a boring day, but you could do it. But then like this F5, I mean, like this is a very, very big number. There's 10 digits in that number. And you could check this as composite in a day, but only because sort of you'd get lucky because sort of one of its prime factors is pretty small still. One of its prime factors is 641. Like if you wrote down a general 10-digit number and just sort of started factoring it, like it'd take a while to do all those divisions. I guess you could do it, but it'd be wild. And then sort of in F6 is going to double the number of digits again. So, and because sort of you have this sort of double exponent here, sort of if you think about it, each time you go from like n to n plus 1, you're going to double the number of digits more or less. Not on the nose, but close. So in really, yeah, so I wrote that down here. The nth Fermat number has about 0.3 times 2 to the n digits. So this is sort of, these get very, very big very quickly. So it's not a good idea to sort of try brute force, just dividing by numbers until you sort of see whether it's prime or not to check this. But we have a theorem, just sort of like the Lucas-Lemmer test for Mersenne primes. We have Pepin's test for Fermat primes. So this says for n at least 1, Fn is prime if and only if 3 to the Fn minus 1 over 2 is congruent to minus 1 mod Fn. Okay, and this is somehow a much easier thing to check once sort of Fn gets very big. I mean, you're raising something to a very large power and sort of modulo something very large, but somehow we know that raising things to large powers isn't really that big of a deal because we can use the method of successive squaring. So somehow like it is still pretty, this works still a lot better than just trying to divide by every number than just doing it by brute force. And you can really verify sort of some very large Fermat numbers are prime in this, or are not prime in this way. That sort of reinforces this expectation we now have that sort of Fn is not prime for any n greater than 4. So I don't know how, it's not actually that high, but we know up to like the 30s at least. These are not prime. Okay, so just an example of how Pepin's test works. So the third Fermat number was 257. So remember this was 2 to the 2 to the 3 plus 1. So that's 2 to the 8 plus 1. 2 to the 8 is 256. You'll know that if you're a computer science major. And plus 1, that's 257. Okay, so to use the test, then we need to compute 3 to the 128. So that's F3 minus 1 over 2. So if we take that minus 1, then we're just left with this power of 2 to the 2 to the 3. So 2 to the 2 to the 3 divided by 2 is equal to 2 to the 2. It's equal, sorry, 2 to the, sorry, 128 here, sorry, is F3 minus 1 over 2. So if I divide by, take off 1, I get 256. Divide by 2, I get 128. Okay. Well, and we can do that using the method of successive squaring. So I can compute 3 squared is 9. Then I square that and I get 3 to the 4th to 81. I get square that and I get 3 to the 8th. If you do that, you'll get 136. Square that and I get 3 to the 16th. Then if you do that, you can write it as minus 8, all mod 257. Then I sort of square that, I get 64. If I square that, I get minus 16. If I square that, well, 16 squared is 256. So minus 16 squared is also 256. So that's congruent to minus 1 mod 257. And that would take me up all the way to 3 to 128. And so, okay, so Pepin's test tells me that 257 is prime. And in general, sort of, if you want to check the nth Fermat number with Pepin's test, you need to sort of square 2 to the n minus 1 times. So you need to square 3, sort of, you need to square 2 to the n minus 1 times starting at 3. All sort of mod this very large number. Okay, so somehow this was probably easier than sort of dividing 257 by a bunch of numbers to do this computation. To check its prime, 257 is pretty small, so maybe they're not so different, but once you start getting up to these bigger numbers, this becomes a much sort of more effective way to check whether a Fermat number is prime. Of course, it sort of has the disadvantage, it doesn't give you a factorization of Fermat numbers, so it just tells you whether it's prime or not. So it's a harder thing to actually find a factorization. Okay, so, and that's Pepin's test, and that's how you use it, but why is this true? So why does this statement happen if and only if Fn is prime? So the first half is easier, and this is where we use quadratic reciprocity. So we have to show two things. We have to show, like, if Fn is prime, then 3 to the Fn minus 1 over 2 is congruent to minus 1 mod Fn. And then we also have to show that if we start with assuming this holds, then Fn is prime. So let's do the first one. First, we're going to do if Fn is prime, then we're going to show that this holds. Okay, so let's just compute this thing, 3 to the Fn minus 1 over 2 mod Fn. Well, okay, so here's where we use quadratic reciprocity. I mean, we have to remember that 3 to the Fn minus 1 over 2, this is just computing the Legendre symbol modulo Fn. So this is sort of Euler's formula for the Legendre symbol. Oh, I wrote that, sorry. I wrote that over here. Euler's formula for the Legendre symbol says this holds. So really, we just need to sort of compute the Legendre symbol of 3 over Fn. And by quadratic reciprocity, this is equal to the Legendre symbol of Fn over 3. So the reason I don't get a negative sign is, well, I would get a negative sign if both the top and bottom were congruent to 3 mod 4. The top is congruent to 3 mod 4. So if I'm not getting a negative sign, what I'm saying is that Fn is congruent to 1 mod 4. But Fn is equal to 2 to the 2 to the n plus 1. And so 4 divides 2 to the 2 to the n when n is at least 1. So that means Fn is congruent to 1 mod 4. So this is quadratic reciprocity using the fact that Fn is congruent to 1 mod 4, so that we know we don't get a negative sign here. Okay, so then I just have to check whether Fn is a square mod 3. So I just have to compute Fn mod 3. And I claim I'm going to get it's minus 1. So it's not a square. So I claim sort of Fn. So if I'm sort of saying this is minus 1, then I'm saying that Fn is congruent to 2 mod 3. So that's the only non-square mod 3. And so why? This is because if I write Fn, again, is 2 to the 2 to the n plus 1, well, that's equal to 2 to the 2 to the n minus 1 squared. So if you work that out, you pull an exponent and it multiplies, it sort of increases the exponent on the inside. Then this gets a little, maybe you can just write this out yourself to see this. This gets a little bit messy with sort of like double and triple exponents, but this is true. So plus 1. So I just rewrote this as this. So that means Fn is congruent to 1 plus 1 mod 3 equal to 2 mod 3. So any square is sort of something not divisible by 3. So any square in F3 cross is 1. So F3 is very easy. If you square something, the non-zero, you get 1. So 1 squared is 1 and 2 squared is 1. So since this is written as sort of squaring something, it's going to be 1. but then I'm adding 1. So what the result is that Fn is congruent to 2 mod 3. So Fn is not a square mod 3. So this Legendre symbol is -1. Okay, that's what I needed to show. Good, so that does the first half of Pepin's test. That says if this nth Fermat number is prime, then it is true that 3 to the Fn -1 over 2 is going to be congruent to -1 mod Fn. Okay, so now we have to show the other part. So we have to show that if this congruence holds, so if 3 to the Fn -1 over 2 is congruent to -1 mod Fn, then Fn is prime. Okay, so how are we going to do this? Well, Fn is some number, so we can always take a prime p that divides Fn. So I'm going to sort of assume this holds. I'm going to take a prime p that divides this Fermat number. And of course, any prime that divides this Fermat number is going to be less than it, or less than equal to it. So if I can show it's also sort of at least as big as it, then in fact, that means this prime will have to be the whole Fermat number. So this is sort of a fun trick that often is helpful in math. To show sort of two numbers are equal, you can show sort of one's less than equal than the other, and also greater than equal to it. And then sort of they have to be the same. So these two things together would apply if p is equal to Fn. Okay, and so then sort of this prime dividing it is the whole number, so that sort of the Fermat number is prime. Sort of funny if you're not used to this kind of argument, but this is sort of a powerful way to argue. Okay, so how does this help? Well, now we know that this prime divides Fn, and we know sort of this congruence holds modulo Fn. But sort of anytime you have a congruence that holds modulo some number, and you take some divisor of that number, then the congruence still holds modulo that divisor. I mean, somehow that's because this is saying this number and this number differ by a multiple of Fn, but sort of any multiple of Fn is also a multiple of any divisor of Fn. So we do have that 3 to the Fn -1 over 2 is congruent to -1 modulo this prime, which is just something that divides Fn. Okay, so we have that. And this is nice because now we're sort of working, sort of even though we didn't assume Fn was prime, like now we're able to work with an equation modulo prime, and that's sort of somewhere where we have some tools to understand things. So let's just rewrite this equation. This says that 3 to the Fn -1 over 2 is equal to, so if I rewrite that, that's 3 to the 2 to the 2 to the n over 2. And then if I simplify and think carefully, this is 3 to the 2 to the 2 to the n -1. And this is congruent to -1 mod p. So we're just substituting the formula for the nth Fermat number to get this. And so the important part is I'm sort of taking this element 3, and I'm raising it to some power of 2. Okay. So the next I'm going to use is sort of a very general fact. In any group, G, so remember the group is just a place where you sort of can multiply, like where you have sort of a rule for multiplying or sort of adding elements. So like FP cross is the group we're going to use here. So the units in FP. But this claims to be true in any group. So if you have an element of this group such that I take this element and I sort of raise it to the 2k power, so I sort of multiply it together with itself 2 to the k times. So not 2k, 2 to the k. So this is a power of 2. And I get the identity element. So in FP cross, the identity element is just 1. But if I sort of raise it to the sort of next lower power of 2, I don't get the identity element. Then in fact, so this G, this element G has order 2 to the k. So that means sort of this is 2 to the k is the smallest power, that divides, is the smallest power of G, such that you get the identity. Okay, but we know sort of by Lagrange's theorem, so we keep on coming back to Lagrange's theorem. We sort of know by Lagrange's theorem that's the order of any element divides the order of the group. So this is, so in particular, in this case, the order of the group is bigger than 2 to the k. So this part's Lagrange's theorem. Okay. So we're going to apply this to G equals FP cross. So G equals FP cross. So P was this prime that we were using before, dividing the nth Fermat number. And then we take G to be 3, and K is this 2 to the n. Okay. So why does this apply? Well, since if I raise this, so I know sort of that if I raise it to the 2 to the okay, you just went through a time warp because I had to pause it to fix something on my slides because I got confused because I'd written the wrong thing. So I was starting to say we should be applying it to K equals 2 to the n, but that was because I just had the wrong thing written down here. So we're going to take K to be 2 to the 2 to the n. So, I mean, up here, we sort of have right, so up here, so we have that one lower power, so 2 to the 2 to the n minus 1, 3 to the 2 to the 2 to the n minus 1, this can go into minus 1 mod p. So we have this sort of first part that this is not equal to e. But this on here. So if I square both sides of this equation, I get 3 to the 2 to the 2 to the n here, and this is just congruent to 1 mod p. So as I'm squaring, we'll multiply sort of this thing by 2, which will sort of put this one more power of 2 up here and get you back to 2 to the 2 to the n. Sorry, it's very easy to get lost in these exponents, but you can sort of just, if you write this out for yourself, you'll see it. Okay, but so this verifies both the statements of the claim. So if I sort of take so K is 2 to the n cert. Okay, I screwed this up again. I'm sorry. K should be equal to 2 to the n. So you're raising to. So what I had written before was right. I just sort of can't parse all the exponents. So raising to the 2 to the 2 to the n power. Okay. Right. So this 2 to the k becomes 2 to the 2 to the n, which is what we had up here to get 1. And then sort of 2 to the k minus 1 is this 2 to the 2 to the 2 to the n minus 1, which is congruent to minus 1. Okay, so which is not the identity element. Okay, sorry about that. But if you're still with me, that means we can apply this claim in this case. And so we get that sort of the size of the group FP cross, which is just P minus 1, is at least 2 to the 2 to the n. So K is 2 to the n. Okay, and so then just add 1 to both sides. I get P is greater than or equal to 2 to the 2 to the n plus 1, which is the m Fermat number. And that's what I wanted to show. So I already knew P was less than or equal to m Fermat number. Now I know it's greater than or equal to m Fermat number. So it actually has to be that m Fermat number. So that sort of m Fermat number is prime. So I've sort of established the second half, except I haven't told you why this claim is true. So let's talk about this claim. So let me just recall one part, sort of one statement that we've used before, like when we were talking about Lagrange theorem, but it's sort of worth repeating. So if you have some element in a group, and if you raise that to some power, then sort of always the order of that element divides, sorry, if you raise it to some power and you get the identity element, then that means the order of that element divides that number m. So some of the order is the smallest power you can raise G to get the identity element. And then any other power you can raise it to get the identity element is always a multiple of the order. Okay, so in this claim, we're saying that g to the 2 to the k is equal to e, so we get that the order of g divides 2 to the k. Okay, but so that means the order of g is a divisor of 2 to the k, but sort of the only things that divide 2 to the k are just sort of two sort of smaller powers of 2. So 2 to the a for a less than or equal to k. So all we have to do is show that sort of if I take g and I raise it to sort of a smaller power of 2, I don't get the identity element. But say I did get the identity element for some a that's smaller than k, then I could take g to the 2 to the a, which is the identity element now. Then I raise this thing to the 2 to the k minus a minus 1. Okay, that's a whole lot, but if you just multiply the like to simplify this by bringing this in and multiplying it in the interior exponent, that just gives you g to the 2 to the k minus 1, which is the identity element because this thing is just e to the 2 to the k minus a minus 1. And if I sort of raise the identity element to any power, I just get the identity element. So that tells me that g to the 2 to the k minus 1 is the identity element. But we have assumed sort of that's not the case. I mean, that was the other part of the claim, is that sort of this smaller power was not the identity element. Okay. So that's how you explain this claim. So this is sort of quite a powerful tool. For example, and this came up a little bit sort of ad hoc in the worksheet and in the lecture on Thursday. Like, for example, if you want to check something as a primitive 8th root of unity, it suffices to check that sort of its 4th power is minus 1, is an example of a different place we've used this lemma, or this claim. We're also going to use this claim for the Lucas-Lemma test. I mean, somehow this claim is also at the center of how you prove the Lucas-Lemma test. So we'll do that in the Thursday video. Okay, sorry about that mix-up earlier with this k. Hopefully you were able to follow. I encourage you to sort of go just through these exponent simplifications yourself to follow along. That's probably the best way to do it. As you can see, even I get lost when I have like triple exponents. But hopefully you're able to go through them well enough to at least get the idea of what's going on in this Pepin test. And then we'll do Lucas-Lemma next time. Thanks.